Okay, so welcome to a podcast on intermolecular forces. So this is part one. I'm going to do this before your quiz on Thursday, and when you come back from spring break, I'll have another one up. So intermolecular forces, the three that you need to know are hydrogen bonding, dipole-dipole, and London dispersion forces, or van der Waals. And they're in order from very, very strong to super weak. So these are the strongest attractions, and these are the weakest attractions. So what you have to know that when you actually determine what intermolecular forces are, you have to know how to covalent bond molecules. So in a previous podcast, H2, H2O, H2S. How would you draw those? Okay, so the previous podcast on bonding showed you how to draw these. So all how you draw a bond is called an intramolecular force. Right? Introspective, looking inside yourself. So if you look at H2, you draw H2 like this. You should have that in your head. You should have water looking like this. You should have it memorized. Okay? H2S would look like this also. Okay? And if you look at how I drew those are all covalent. That's the intramolecular force in them. They are covalent bonds. This is nonpolar, this is polar, and this is polar. Why are these both polar? Because there's dipoles. Why are they also polar? Because there's lone pairs on that middle element. There's no middle element here. Two hydrogens on either side of a rope pulling equally is nonpolar. So let's go back to what these are, these forces. So these are called intermolecular forces. Like you need an interpreter to interpret or have a relationship between two different molecules. Now those two different molecules can be one water molecule and another water molecule. Right? When you drink a glass of water, you don't just have like one water molecule, there you have lots of them. So their interaction between two water molecules is an intermolecular force, an attraction between two different molecules. These are bonds, intramolecular forces, irritating because they use the same word, don't they? Force. Okay, they use the word molecular. The key difference is an intra, inside something, and an inter, between two different molecules. And those are the key words you have to use. And the only reason I say that is because if you talk about hydrogen bonding, what's right in that word? Bonding. It's not a bond. It's an intermolecular force. Okay? So we're going to walk through this 1, 2, 3. I'm going to show you how they work and talk about them in terms of boiling point. So if I was to draw CCl4, CCl4 looks like this. Tetrahedral molecule, and in your brain you should say, oh, hey, that's got dipoles, but the whole overall molecule is nonpolar. So whenever I ask you what are the intermolecular forces and explain them, then you would have to draw two different molecules of the same sample. Okay, so intermolecular forces of CCl4. That might be the question. And describe them and talk about them and compare them to the other ones. So I need to draw two molecules of CCl4, tetrahedral, nonpolar, and I know that this is nonpolar. So I would say, okay, what do I know about this? I know that these are nonpolar covalent molecules. And if you and I know it's nonpolar, you can put NP. They're both nonpolar covalent molecules. There are dipoles, but overall they cancel. You would actually have to draw those dipoles. Oh my gosh. Okay, draw them all. Put all your partial positives and negatives. Pain, I know. Hard for me to read and grade too. Okay? Positive, etc. Okay? And in reality, what's true about these? If the dipoles all cancel, then these really don't look like anything except for a big blob of electrons. It's this huge electron cloud. Okay? So that's all they look like. Right there. So if that's what they look like in space, make this eraser bigger, then what would happen if an outside force came nearby? I mean, if they're just a cloud of electrons running around, what would happen if this blob and this blob had some kind of negative force come by here? Or if all of a sudden, for some reason, this one just shifted. I mean, electrons are going on a cloud. Why can't they all go on this side a little bit? If they do that, and a bunch of electrons are on this side, and there's less electrons on this side right here, this side's going to turn positive. And this molecule that's right next to it is going to go, oh my gosh! And all the little negatives are going to this side. So this is where all the negatives are. And all the little positives will be on this side. So either by an outside force or just spontaneously. And look what that forms. Oh look, it's a dipole. How about that? And just as easily, it can go away and form two blobs again. So it's now you see it, now you don't. And if you look, here's a picture of it. Nope, wrong one. There you go. And I can't annotate over this because it's on the internet. But if you look, this is a van der Waals attraction. You can see that there's a word fluctuating there. There's a chance charge separation, and the molecules actually form a fluctuating dipole. An induced dipole. It's temporary. And so for just a moment, there's a weak attraction. And that weak attraction is called van der Waals. We also can call it London dispersion forces. And so this force of attraction right here, between one nonpolar molecule and one nonpolar molecule, and remember, these were both CCl4, weren't they? This attraction right here is called a London dispersion force, a weak attraction between two nonpolar molecules. So if it's a weak attraction, these are going to boil very easily. Okay? Now, what if I had this situation? What if I had molecules that were small, like a sample of H2, right? That's nonpolar covalent, isn't it? Right? Nonpolar covalent, nonpolar covalent, blob and blob. And then CCl4, I'm not going to redraw it, but let's say this is CCl4. I think you'd agree with me that CCl4 is a lot bigger molecule than hydrogen is. So what's true? If they're nonpolar, right? This is nonpolar covalent, this is nonpolar covalent, big sample of hydrogen. Nonpolar covalent, nonpolar covalent, big sample of carbon tetrachloride. Which one has a bigger attractive force? I would say this one hands down. So what's true? This boils easily. Why? This is a London dispersion force, which we also call van der Waals to honor the man who figured it out. And this is also a London dispersion force, or van der Waals. But guess what? This is a smaller attraction. There's less surface area. Those are the key words I'm looking for. Less surface area. And so since there's less attraction, this also boils easily. But which one boils faster? This one does, because there's less attraction, almost like a piece of sticky tape here. I could take that tape away. This would take me a lot longer to peel these guys apart. So they both boil easily compared to other molecules because their forces of attractions are weak. They both have London dispersion forces, or van der Waals, but this is really wussy and this is less wussy. This is a stronger, weak force. It's an attraction between two molecules. All right, let's move on to dipole-dipole. I wonder what dipole-dipole is. Well, gee, there's the words dipole and dipole. So guess what? This must be a polar molecule and another polar molecule. So let's use H2S, since I drew that before. This is what H2S looks like. S is in the same column as water. Okay, so I'm going to go ahead and draw one first. I'm going to put dipoles in there. S's happen is this molecule would flip and it would look like this.